Hello again and welcome to another lecture on mechanics in which we will solve a second example related to the design of beams. However, before we do that, I would like to show you two simple cases in which we can very quickly determine the maximum bending moments in beams, or we can even remember that value. So the first case would be for a simply supported beam, which has a point load, a concentrated load, located at its midspan, so at the middle of the beam. So in this case, this would be the load at the middle. Let's say it has a magnitude of P, and it is located at half of the span from either end. And in order to quickly draw the shear force and bending moment diagrams, we need to solve for the reaction forces, which are easily determined by inspection due to symmetry of the dimensions and the loading. So half P on the left end, half P on the right end. And once we know the reaction forces, we can draw, as I said, the shear force diagram as well as the bending moment diagram. So very simple, the shear force diagram will be positive and constant on the left-hand side of the beam and negative and constant on the right-hand side of the beam, having magnitudes of half P and negative half P respectively. Obviously, if the shear force is constant, the bending moment will vary linearly. It will be equal to 0 at the pin and roller ends of the beam and will have a maximum at the midspan of the beam. In order to determine the maximum value, we can use the property that the change in moment from the left end to the force equals to the area under the shear force diagram, and hence from here the maximum moment will result as equal to P times L, the span of the beam, divided by 4. Very simple relationship. The second case that I would like to present to you is of a simply supported beam that has a uniformly distributed load all along the entire beam. So again, this would be the beam, and the load will be applied along the entire length of the beam, not just part of the beam, the entire length of the beam. So it's uniform. It will have a constant load intensity of, say, W. The span of the beam is L, and we will follow the same procedure to determine the shear force and the bending moment diagram. Again, the reaction forces are straightforward to calculate because of symmetry of both the geometry and the loading. So both vertical reaction forces will be equal to WL over 2. And once we know the reaction forces, we can draw the shear force diagram. The load is positive and constant, so the shear force will vary linearly with a negative slope of W. So we start at plus WL over 2, and we will end on the right-hand side at negative WL over 2. Again, the slope of the shear force diagram will be negative W. Then we can draw the bending moment diagram, recognizing that the shear force is 0 at midspan, and therefore the moment will have a maximum at that location. Since the shear force varies linearly, the moment will be parabolic, and we'll start with a positive slope at the left end due to the positive value of the shear force, and we'll end up with a negative slope on the right end due to the negative value of the shear force. If we now calculate the maximum moment using the same principle, the relationship, the formula that we will obtain will be WL squared over 8. WL squared over 8. So these two are very simple relationships that can be easily derived, as you can see, or in many cases, because they're so common, they could be simply memorized. So now let's go to the actual example. in which we have indeed a beam like in the second case on the previous plate. And this is a simply supported beam having a span of 3.5 meters, which is loaded by a uniformly distributed load all along its length, having a magnitude, a load intensity of 3 kilonewtons per meter. Now, if we were to cut the beam at some point along its length and then draw the resulting cross section of the beam, so that would be section AA, the beam would be rectangular as shown, with the largest dimension vertical, the horizontal dimension being A, the vertical dimension being B, and we know as a condition that the depth of the beam is 3 times the width of the beam, so B equals to 3A. The beam material is wood with an allowable stress of 12 megapascals, and the load factor for bending in this case is equal to 2.0. So we need to determine the dimensions of the section for this beam. So in other words, we need to calculate dimension A and dimension B. Of course, again, knowing that B will be equal to 3 times A. So now we can quickly calculate the maximum moment, knowing that this will be equal to WL squared over 8. And this will equal to 4.594 kilonewton meters. That is the specified moment. And then, because this is a design question, we need to determine the factored moment by multiplying the specified moment by the load factor. And this will give us a factor moment of 9.188 kilonewton meters. Then we can calculate the maximum stress developed in the beam due to the applied force. The beam is bent, as you can see, about the x-axis. So the forces are perpendicular to the x-axis. The distributed load is perpendicular to the x-axis. So therefore bending occurs around the x-axis. So we need to use in our bending formula the second moment of area about the x-axis, so Ix, and also we need to measure Y max in the vertical direction from the x-axis to either the top or bottom extreme fibers of the beam. So if we do so and we plug in the numbers, of course we do not know the values of Ix, so we can express this as A times 3 times A, which is B to the cube, divided by 12. And then Y max is half of the depth of the beam, so half B, or 3A over 2. And the entire expression must not exceed, so the actual stress in the beam must not exceed the allowable stress in the beam, or otherwise the beam would fail. And the allowable stress is equal, of course, to 12 megapascals. So all we have to do from this expression, solve for the parameter A, dimension A, which will result 79.9 millimeters. We would obviously round this up to 80 millimeters to get dimension A, because this is wood and we cannot cut it that precisely, and multiply it by 3 will give us dimension B. So our final section will be 80 millimeters by 240 millimeters. And this is what we can use for this beam, given what was required. 80 millimeters by 240 millimeters. So thank you very much for attending this lecture, which concludes the chapter on the design of beams. Of course, I will see you at the next lecture.